Okay, thank you for stay. Now let's go begin the 12th presentation of this conference. We begin in the organization. Let's go make all presentations. In the end, the questions for all presentators. We begin with the computer vision analysis of BIOSLUDGE characteristics during process shutdowns in pulp and paper industry activated sludge plants. Heikki Hannukainen. Okay? The floor is yours.
So I come from a company called Toihan, and today my topic is about BIOSLUDGE structural analysis with computer vision. And where I'm focusing today is, of course, the behavior during production shutdowns. To start with a few words about Toihan, we are 11 years old consultancy business located in Helsinki, Finland. We focus on improving wastewater treatment process control, and mainly within pulp and paper industry with board mills. And depending on how you calculate, I would say 60 mills. My colleague says 50 mills, but I'm always a bit more optimistic when I calculate things. But with many mills, of course, main focus in Northern Europe, Finland, Sweden, Norway. And the nice thing, of course, everything is related to one big sustainability topic here. But when I come with this computer vision analysis, it's kind of going also towards artificial intelligence, how we can utilize AI to improve process sustainability. And I could give another lecture about this graph, but the whole idea with this sustainability curve that I'm presenting is that when we purify water more, we of course use more chemicals, more energy, and after some point we don't necessarily minimize the environmental load anymore. We start to create new environmental load. So there is some kind of sweet spot to be found. And we think that with better decisions, faster actions, we can affect these sustainability curves. And this is pretty much about that, how we use computer vision. And why we want to use it, it's a long story, but if we take a look at the BREF documentation, best available technologies, they have listed that microscopic examination of BIOSLUDGE is a one way to monitor and prevent process upsets. And it's usually made in laboratory by human, by eye. So with this kind of tool, we can give more info to interpret that change or that structural quality that we can see in BIOSLUDGE. And I have talked about this before, also in Tecnicelpa, and thank you again for having me here with the same similar topic than last time. It's always a pleasure to be in Portugal. But this kind of idea, why we want to use computer vision is that we can extract data from those images with timestamp. So it becomes not only an image data, it comes numeric data with timestamp. So it can be combined with other process parameters, other variables that are contributing to this BIOSLUDGE generation or formation in activated sludge process. And the whole idea of wastewater treatment is to convert dissolved material into suspended solids that can be separated from the water. And with BIOSLUDGE, especially in activated sludge processes, the separation is by settling in secondary clarifier. So it means that this BIOSLUDGE settling characteristics has a big impact on the process performance. And this is again good thing to remember. And why I chose this process shutdown, production shutdown time period is, of course, because we see a lot of changes in biosludge when we don't have incoming wastewater. The biosludge that has been grown in aeration basin stays in rotation, and it starts to decay by microbial activity. So we are kind of we see the structural change. So this makes it very interesting to apply computer vision over production shutdowns. And these images were collected in 2 mills. I had paper mill and pulp mill, and the laboratory personnel did the sampling and imaging and analyzed that with FlocMark application. And what the application does, it kind of tries to identify as much object categories as it can. So in this image, this is an idea. You can see biosludge flocks. Flocks are those big round ones. Then you can see filaments. Filaments are like those thin lines that usually are there, but the excessive growth of filaments may interfere the settling again. So if we have too much filaments, we may lose some biosludge in secondary clarifier overflow. And that's, of course, loading more the water base. So we capture all these categories and analyze them as much as we can. And it's an image analysis, so it's big pixel analysis, of course. So from flocks, we get flock size, flock porosity, flock density, filaments, the area, the amount of biomass that were filaments. We also have filament webs if they are like forming webs, so and fine particles that we see. And the flock is the main product we aim to grow in these processes. And this is an example image from my colleague's presentation, Sakari Toivokainen. And this kind of explains the porosity or density, how it behaves. And what we want to see, of course, are those big flocks that with good density. And the lighter those flocks become, the less they settle, or the risk of carryover increases. So on the right hand side here, these are not that well settling flocks. They can settle, but this is of course better. And in this kind of two mills I chose because I wanted to point out that this is not only one phenomena at one mill. It happens almost every time. So I have paper mill, mechanical FIBRELINE production, short shutdown, production shutdown 5 days. Then I have pulp mill, ECF kraft pulp mill, and that production shutdown lasted for almost 4 months. So it was really long one. Of course, I had some other parameters that I will use, sludge concentration and SPI, but this is pretty much what I'm showing. And this is a nice way to present. I will always show you one mill, and then I will show the other mill, and then it repeats itself, so you get familiar with the presentation quite easily. So I will start with the filament behavior, and on the left-hand side, here is the organic load to wastewater treatment plant expressed as kilograms of COD per day. And when it goes low, we can see that black line drops. It means that there is no organic load entering the wastewater treatment plant, and the shutdown period is that green area pretty much. So what was registered? Of course, we can, maybe these are too small images here. You have filaments, and on the lower image you don't. And we can see that also in image analysis, those blue lines drop. So filaments cannot survive without food, pretty much. Flocks can survive, so it's an interesting observation. And this was short period. And after production increased, the filaments didn't reappear immediately. So I don't have enough time to explain why they were there, but this is how they behaved without food. And longer shutdown also. This was a bigger pulp mill, and I have similar COD load as black line, and then filaments with blue. And they all disappear within the first days without any food, which is good. But then again, it's not selective. It's, of course, the longer shutdown we have, it starts to affect the flocks as well. It's not only the filaments. So when we have this kind of sludge decay, it can be expected that the flock size decreases. So the bigger flocks become smaller because they break down during that shutdown. And what happens when big flocks break, they release fine particles, smaller particles that can be seen also in water by eye and also with this image analysis. So pretty much makes sense. It's what I see by eye, but now I have them as numbers. And longer production shutdown in pulp mill, similar degradation effect. Flock size decreases, fine particles increase. And of course, with fine particles, we can expect that the carryover from secondary clarifier increases suspended solids load to environment. So in that way, it's not good to have much or high number of fine particles. But this is a phenomenon that happens. And what happens with porosity, if we think about that we have dense flocks, they break, they become more open. So when we have sludge flock decay, the size decreases and the porosity opens, so it increases. So we have smaller flocks which are more open. And my colleague will present here also a poster. There is this also effect of how this porosity contributes to settling. So it's quite interesting. It's another feature, not only filaments. But this makes sense with both long and short shutdown, production shutdowns. So we have a way or method to evaluate flock formation over time. And when we think about why we should track down filaments, they always indicate of something that we don't want to happen. If we have too high amount of filaments, there might be lack of nutrients or oxygen or something negative affecting the flock, good flock growth. And this is with sludge concentration laboratory analysis, mixed liquor suspended solids, so MLSS, referring to sludge concentration in aeration basin. So when the flocks decay or biomass decay, it decreases the concentration, which is quite logical, and fine particles appear. So same story again. And how we know this from earlier studies as well, that the less filaments we have, the better the sludge settles. So we have not with this one, we have really fast way to get rid of filaments, but it might be really expensive for pulp mill to stop production to get rid of filaments. But it's quite fast. And SVI, sludge settling parameter, the lower the SVI is, the better. So we can see that settling improved when we got rid of filaments in paper mill case. And similar drop with pulp mill. There is this is of course 4 months period. They are emptying a lot of reactors and lot of stuff from emergency basins and sometimes foaming. So of course these all are affecting SVI. But if we take a look at the big picture, we can see that decreasing of filaments is also improving this SVI. Exactly what I expected to happen. And with this kind of info, if we think about how mills can utilize now this kind of information in their daily operation before production shutdowns. If we think about that, okay, the filaments will disappear really fast. So maybe we don't need to overdose nutrients day or 2 days before the shutdown starts. it's not necessarily a good thing to overdose nutrients before shutdown. It's less harmful to dose less nutrients before shutdown. Nutrients will increase their levels when the flocks decay. So every time during shutdowns, we measure increase of nutrients in water. So even if we were growing filaments for 1 day or 2 days, they will disappear during shutdown, and we might have an opportunity to reduce the nutrient load to environment. What I have seen with many mills is that pretty much, I would say, up to 30% of annual wastewater treatment load originates from production shutdowns. So if we can find new ways to reduce environmental load with better strategy in activated sludge process, we might be better off. And this is how AI is helping us to cope with and collect new info. Yeah, but thank you. That was pretty much my story today.
Thank you, Tim. The questions in the end of the presentations. The next presentation, the theme is reuse of process stream in the FIBRELINE, use of condensates and integration of pulp and paper circuits. It's backed by Isabel Pinto, graduate in chemical engineer and holds in environmental engineering from the Faculty of Engineering of University of Porto. Between 2009-14, she was involved in research activities at the university, and in 2015, she joined RAIS, where she currently works in the technological consulting team, which supports projects from the industrial departments of the Navigator company, such as a process, pulp and paper, environment, and energy. The floor is you.
Thank you. Thank you for the presentation, and thank you for the opportunity for being here. I'm going to start with the motivation for this work, which is the water efficiency in the pulp and paper mills. This subject was already mentioned in one session this morning, but I'm going to reinforce the message that we need water in all our operations, whether in pulp and paper mill. But we are dependent on the water availability and water quality, and also on legal requirements for total volume withdrawal and wastewater discharge. In the Navigator company, we have a global program for reducing water that involves all the mills, and we have lots of ideas. Some of them involve reusing streams from one point of the process to another. This has risks, and before we go to the mill and do these measures, we have to take into account these risks, and we can try to account them, whether by computer simulation or in the laboratory. And today I'm going to present you 2 cases of laboratory work that tries to assess these impacts of reusing streams in the pulp and paper industry. So the first one is the reuse of secondary condensates. The water evaporates from the black liquor in the pulp mill and forms these condensates. Yeah, this is a bit too high. And they are usually contaminated with organic volatile compounds such as methanol and acetic acid. And we already use these condensates in some points of the process. In the washing of the unbleached pulp is a well-established practice, but in the bleaching is not so conventional. So we tested condensates in the bleaching sequence, and then we try to monitor chemicals consumption and the pulp properties and see its impacts. And the second case is the integration of paper processed water into the pulp mill. This obviously for integrated mills. And it's a challenge, especially if the mills are producing multiple products. For example, if a mill is producing paper, copy paper, printing and writing paper, it uses several chemicals in the process. One of them is the optical brightening agents, or OBAs. These OBAs, under the UV light, give fluorescence, and they are used to enhance the brightness and the whiteness of these paper products, but we don't want them in the market pulp if this market pulp is produced in the same mill. So that is the challenge for the integration of paper water into the process of producing pulp. To try to mitigate this OBA issue, we tested several chemicals, mainly oxidants, to degrade the OBA and also solar radiation. And then I'm going to proceed with the first case, the reuse of secondary condensates. We got the pulp from the mill after the first chlorine dioxide stage, and then we simulated the rest of the sequence in the laboratory. So the first alkaline extraction, then 2 chlorine dioxide stages, each of them followed by a washing step. And it was the liquid to wash the pulp after the alkaline extraction that was submitted to study. We collected 2 condensates from the mill, so condensate A and condensate B. Condensate A a little less contaminated, so lower COD, chemical oxygen demand, and condensate B more contaminated, mainly due to methanol, not so much due to black liquor contamination. As you can see, the sodium concentration is similar between them. And we test these liquids to wash the pulp after the extraction stage from hot water to condensate B, different mixtures, different condensates with increasing COD in this direction. Then we analyze the pulp properties, the filtrates, and the main conclusions are here, the main results. So the kappa number after the washing of after the extraction stage increased almost linearly with the COD of the washing liquid. So a dirtier washing liquid increased the kappa number after this stage. But after the full sequence, the properties of the pulp were mainly unaffected. So I'm talking about brightness reversion, and viscosity. So that's good news. Then the chlorine dioxide consumption for the 2 chlorine dioxide stages after the alkaline extraction, so after we use the condensates, we concluded that the chlorine dioxide consumption increased because we are spending chemicals in oxidizing the organic compounds that are present in the washing liquid besides the one present in the pulp. And we calculated an additional of 0.23 kilograms of active chlorine per kilogram of COD in the washing liquid. So we have quantified the impact of this reuse. So for this part, the advantage of applying this measure is to reduce water. We have some risks of closing the circuits, like always in this kind of measures. And we have the increasing chlorine dioxide consumption. We quantified, so we can make an informed decision of whether to save water and increase the costs, and at least we have the numbers and we can calculate the trade-off between them. For the second part, which is the integration of paper water into the pulp circuits, we tested chlorine-based oxidants first. So chlorine dioxide and sodium hypochlorite in clarified water, so processed water from the paper machine. As you can see here, clarified water has a lot of chemicals that are used in the paper production. The OBA is giving fluorescence under the UV light, and that's what we are trying to mitigate. So we add these oxidants in the clarified water, in the real water, and we prepared pulp sheets using this liquid, as you can see here. If we prepare a pulp sheet with pure water, it doesn't show any fluorescence, but if we prepare them with the real clarified water or a pure OBA solution, we can see that they have fluorescence. So we analyzed the pulp sheets obtained with our solutions to check if they had fluorescence or not. And as we increase the chemical concentration, whether chlorine dioxide or sodium hypochlorite in the solutions, we can see that we have a decrease in the fluorescence, both in graphic and by analyzing them. which is what we wanted, up to the point where no fluorescence is left. So at least they were effective in dealing with the OBA. We also tested other chemicals like hydrogen peroxide and ozone. This time we add them to the solution, a pure OBA solution or the real clarified water at controlled temperature, pH, time, and then we analyze the liquid by spectrophotometry at a wavelength of 350 nanometers, because we saw that there is a linear correlation between the absorbance at this wavelength and the OBA concentration. And similarly, we tested solar radiation, so we exposed these solutions to the sun by a window, and again checked the absorbance at this wavelength. Hydrogen peroxide, not very effective. The absorbance almost didn't vary, so hydrogen peroxide alone doesn't seem to do the job, even when we change the pH. Ozone, by the other side, very, very effective in a pure OBA solution, not so much in the real wastewater. Here we have a more complex matrix with the organic chemicals from the paper production and colloids, and probably not the optimized conditions for that. We are still working on that with some academic partners. By exposing these solutions to the sun, the OBA, by checking the absorbance, seems to be removed effectively, but we are talking about 75 to 90 hours, so not a very adequate time for an industrial process. Anyway, with these solutions obtained after exposing them to the sun, we did some pulp sheets to check if this decrease in the absorbance resulted in decrease in the fluorescence in the pulp. And yes, compared to the liquids that were not exposed to the sun, the difference are visible. So how can we integrate the paper water into the pulp process? One of the ways is to use the clarified water to wash the transferred pulp from the pulp mill to the paper mill. The disadvantage is that we will have the paper chemicals, including the OBA, in the filtrate that returns. So the pulp that is not coming to the paper machine, but yes to the pulp machine, will have OBA if we are producing market pulp. That's not what we want. If you were in the session this morning, from the navigator, you see that we are already doing this, but we can't do that if we are producing market pulp to sell to external customers, because we can't have the OBA. So how can we mitigate it? We could use chlorine-based oxidants, like the one we tested. We saw that they are effective. However, we are increasing chemical costs, and we have the issue of chlorine levels that may affect the process and the equipment, especially in the paper machine that is downstream the process. Another way of doing this is, instead of using the clarified water in this point, we could use it to replace, for example, hot water in the extraction stage, like we tested for the condensates. And then we would have chloride dioxide stages to remove the OBA. We also tested this in the laboratory, and it was effective. If we wash the pulp with clarified water and then have chloride dioxide stages, then we will not have fluorescence in the final pulp. So basically, here I showed laboratory tests to assess two ways of reusing streams from one point of the process to another, trying to identify and quantify its impacts, so we can make informed decisions of whether or not to save water for these two approaches to reduce water in the FIBRELINE. Thank you very much for your attention.
The next presentation is made by Kraig R from the United States operating an energy efficient and sustainable pulp mill. Kraig from Mankato State University graduated with a Bachelor of Science degree in Mathematics, Physics and Computer Science, obtained the Master of Science degree in Nuclear Engineering from the United States Naval Postgraduate School. Entered the pulp and paper industry in '93 at member corporation Aztego, Michigan, mill service as wood paper machine and pulp and recovery team loader. Moved to Georgia Pacific in '99, filling roles as pulp mill manager, power utilities manager, and production manager in various facilities. Shifted to the role of global application manager for pulp and paper recovery systems for Hercules in 2008, and then to Nalk Water and senior global industry technical consult for pulp and paper recovery areas into 2014. Primary role is in the optimization of mill system, development of new grades and technologies, and optimizing the use of specialty chemicals to the process goals. Kraig, the floor is you.
Thank you. This is going to be a very different presentation probably than you all have had for the last day and a half. This is designed more to make you think. One quick question for everybody here. How many of you are directly involved in the operation or the management of a pulp mill? Okay, we have a bunch. Good. I am not going to show research. I am not going to show any of this. I have been working in pulp and paper for almost 40 years. And when sustainability started to come around, started to show up many years ago, there's been a lot of attempts to fix. And what I want to talk about today is a little bit different approach to that. How can we operate? And I'm going to use real world examples of some of the things that I'm talking about. In my role, I travel globally. My job is to optimize the operation of mills all over the world. Spend a lot of time, obviously, in Brazil, starting up new mills, changing mills, optimizing mills. And so what I really want to talk about today is how do we get about operating in a sustainable way fully, not our public persona of sustainability. How do we really do it? Okay, I was going to put a subtitle on this. It was going to be called Sustainability, Welcome to Reality. Okay? So there's a big difference between sustainability and centerlining. And this is something that I want to talk a lot about. Many times we are actually anti-sustainability by being pro-centerlining, okay? So we'll talk a little bit about that. Liquor chemistry control, addressing variability. These are all absolutely critical for our mills to operate in a sustainable fashion. So these are the areas that I want to focus on today. I love this graph because I think everybody here believes they understand what sustainability is, okay? And sustainability really is how things come together. I have to be an environmental steward. I have to take care of my social responsibility. The biggest circle, the blue circle here, probably should be the biggest because none of us work for a charitable organization, okay? The idea is everything I do must be profitable, okay? Every time I hear people talking about sustainability, there is a cost. By definition, I am no longer sustainable, okay? So this is really, we need to take a hard look at this. Obviously, we're not going to go to the public. We're going to go to the public and say we're going to save the rainforest, right? We're going to reduce our water consumption. This is what is public consumption. I am not going to go to the public and say, and I'm going to make money doing it, okay? But that's the reality. That is the reality, or none of us will be here next year, okay? So where do we start? Obviously, number one thing I have to do is I better understand what my current and future customers that I want are asking for. And then I have to get there, okay? I have to know my process, honestly. Every time I go to mills and I ask people, I'm running great. Really? You know, you're designed to run here. Why aren't you pushing it further? But I'm running great. You know, no. You have to be honest about where your weaknesses are. You have to be honest about the variability in your system. This is where we start. Look, take the hard look and be very, very honest about where you're at. Okay? Do we actually monitor the things we should monitor? And if I monitor them, am I using them to make decisions? If I'm not, why are you monitoring them? Okay? So we have to make sure that we are looking for what we want to and need to look at. And that should be your focus. Everything you monitor, everything you measure should be part of your decision-making process. Absolutely should be, or you're wasting your time. Okay? Where is the variability? I get told all the time, but that's normal for these mills. Just because it's normal doesn't mean it's right. Okay? So, you have to be hard on yourself, honest with yourself if we really want to improve. And are we documenting repeat problems? If it's something that happens more than once, do we know why? If not, we better find out. Okay? How many of you that just raised your hands that you were involved in mill operations have done some form of center lining in your mill? Come on, you all did. I'm sure you did, right? To what degree? Some do it a lot. Some don't do it quite so much. But many, many times I induce variability by center lining. Okay? How many of you have perfect wood every day? I've never seen it. I quit fighting about it, okay? But if I now center line the rest of my mill to be flat and I have a variable raw material, guess what? The end result is variable. I don't want to be center lined. I want to center line on key variables, not the little variables, not what's easy, okay? So this is what I'm talking about. This is one I love to see. How many of your recosticizing areas, if you have more than one boiler, have a stabilization tank, something like this, and you've optimized it, it's flat. Man, I can control this level all day and there is no deviation. You know what it's designed to do? Vary. Okay? You just took out what it was designed to do. But you know what? These are easy to do. These are single point controllers. I can do this all day and I can go report to somebody, look at how good my control is. And I just induced variability and raised my cost and reduced my CE variability or stability. Right? Why do we do this? And we all do it. Every mill I go to does it. So don't focus on those kind of things. Okay, here's another example. This mill was very, very determined to improve their center lining. They center lined their kiln temperature profile. And it was one of the best I've ever seen. This didn't vary for anything. It was so solid. It reacted quick. It was, oh my gosh, it was beautiful. And the whole time I was adding more and more and more lime to my green liquor because I was overburning. Okay? Is that sustainable? Come on. And they were looking at their own graph and asking, I wonder why that is. You know? Think about what we're doing. Think every step what we're doing. And is it make sense? Okay? We have to stop doing these things because they sound good, because other mills are doing it. Okay? We have to get away from that. Okay, so what should we be stabilizing? What should we be working to center line? How about things that cost money? If I have to be profitable, I better work on the things that cost real money, not the fake stuff we like to calculate, okay? What cost you money? Wood. So what do I want to try to stabilize? Wood consumption per ton of pulp, okay? Final sellable product per ton of digester production. I can't lose it in screening. I can't lose it in bleaching. How do I deal with that and get the most possible to the end of the line and sell it? Reduction efficiency, costicizing efficiency. This is real money. Real money. Those are what we should be center lining. All the things that we center line are your operating levers to get these. Okay? So we have to I'm not saying don't center line, I'm saying center line on the right variables. If you're centerlining something that doesn't cost you money, you're probably on the wrong variable. Okay? There's two main hidden costs that hurt us day after day in mills. One is variability, and the other is very poor liquor chemistry in general. Okay? They're always higher cost, higher energy, reduced quality, increased consumption of raw materials. They cost me money 100% of the time. And those are the things that we need to focus on very hard. Okay, I could actually talk for weeks on this, but I have 15 minutes, so I'm going to try to keep it short. Okay, here's a mill. This is a very, very proud mill in Brazil. Okay, I will just narrow it down that far. Okay, that's their kappa variability. Not good, right? So what did they centerline? Liquor injection temperature on the recovery boiler. Okay, I know my organics are swinging all over because the kappa's terrible. And I changed 5 degrees in 2 years. 5 degrees. You know what their reduction efficiency is? It's horrible, right? It's horrible. All I did was say, let's fix this and let's let this vary and adjust it. And our reduction efficiency went up 5 points. We saved millions in sulfur makeup by not centerlining, by operating, right? Unusual concept, I know, but it's not. It's not. It's going back to operating. That's what we have to be good at. Okay, another mill in Brazil. They had to make more yield. They had tried increasing increasing kappa. But, of course, anything I gained at the digester, I lost through shrink in the bleach plant. I lost in O2 delag. At the end of the day, they were actually making less pulp by raising kappa. So we actually helped them out with the way they cooked. We changed the way they cooked. I do work for a chemical company. We used a chemical to help. Okay? For the same digester production, less negative 0.6% digester production, I had 8% more pulp going to the machine. 8% because of stability, because of lack of loss in screens, because of less aggressive O2, less aggressive bleaching. The kappa variability was not statistically changing at all. There was no kappa change for this. It was just how I cook. Okay? 8% yield, basically, not what we normally call yield, but total yield by doing nothing but fixing the process. Okay? Do you think that's worth money? You know, that was a 3,500 ton a day line. 8% more. Do the math. Okay, liquor chemistry, on the other hand, is something that I think we know, but I don't always think we know what to do about it if we have a problem. Okay, you can have two problems. One is non-process elements. We love to use that term. And that's kind of like the catch-all for everything that I can find in my liquor. We also have too much or not enough process elements. I can have too much, not enough calcium. It's supposed to be there. I can have too much or not enough carbonate. It's supposed to be there. Okay, we all know about having chlorides, potassium. We talk about that all the time. What if I have too much carbonate? Okay, it's a problem. It's a huge energy cost for one. Okay, another mill. These guys were, again, I like to show some because when I start asking questions, these mills are very proud of their results, okay? So this was a mill that we started talking about non-process elements, and their answer was, we have that covered. We're good at it. Okay, where are you at for lime availability? They said 91%. Okay, 91%. Not bad. Could be better. So, again, what should we do about that? We want to improve it a little bit. There's money there. I want more lime in my lime. So how about if we work on temperature profiles and fix some of the things they did? They did. And the more they worked on it, the worse it got. They got rid of magnesium. They got rid of phosphorus. They got rid of sulfur, you name it. Their availability went down to 84. Okay? I lost 7% lime in my lime. by trying to fix a non-process element problem that wasn't a non-process element problem. Okay? Where did it all go? It's carbonate now. They can't control how the lime burns. So I have less lime by trying to fix something that really wasn't a big problem to begin with. Okay? It's not hard to get involved in these projects. It really isn't. You know, I have mills all the time that have pressure filters for white liquor, and their project is to optimize CE. I'm going to raise my CE. I'm going to help myself. Next thing you know, the white liquor filters plug in every day, and they're acid cleaning, and they can't get throughput, and they're adding caustic. And they say, how do we fix this? And I say, put your CE back down where it was. You were fine. You know, yeah, but that's not the industry stuff. Who cares? You're running, you're making money. It's fine where it was, okay? Don't make projects just because it sounds good. But when it comes to liquor chemistry, make sure you're working on the right thing, okay? I get asked all the time about, can you give me a chemical to do something? Fill in the blank, okay? 9 times out of 10, it's actually a process problem, and we try to fix that. If I can't fix it, fine. We'll find a chemical for you. This mill had terrible lime mud solids. It's a mill that has 3 old kilns. All 3 have to run, try to keep up with the lime. They're always short. It's a bottleneck for the mill for liquor production. So they said, we want something to make the lime mud solids higher going to the kiln. So I started to look, and the lime mud, it looks like a dregs filter, okay? The mud was almost black. So I saw that, okay, you know what we can do? How about we fix your clarification first? So we went back and we optimized the clarifier. We changed some things around there, how they were balancing flows and how slowed down the movement of their stabilization tank, like I showed earlier. Okay, all we did was get the dregs out. That's all we did. And we saved over $1 million in kiln gas because the solids came up by themselves. Okay, I didn't need a chemical. I needed to work on the right problem. Okay, still a liquor chemistry issue, still a problem with that, but make sure you've done enough digging in to know what the problem actually was and solve that. Okay, I just wanted to show one really quick case study because as chemical vendors, we're responsible for part of this too, right? I have to be a part of that solution at the same time. I like to call this mill the worst case scenario. Okay, it's a mill in Western Canada. They have 6 grades that they make routinely at non-specific time changes when they adjust. 2 of the grades are unbleached, softwood and hardwood, okay? 4 of the grades are bleached hardwood, bleached softwood, and bleached co-pulped blended pulp, okay? You talk about a mess for a liquor chemistry cycle, right? It's horrible because I got 100 kappa, next thing I know I've got 20 kappa. Okay, sometimes the chips are mixed. The liquor's always mixed. There's no segregation. So this is one, if you want to work on optimization and you want to go to a university to get a doctoral course in optimization of a process, go there. Okay? But they had a lot of issues with quality, of course. Shives, pitch, you name it. So we started looking everything from how we transitioned, how the automation systems in the digester, in the washers, how did they know what they were on? How did we adjust correctly? How did we estimate when I was going to be there to make the next change? We looked at all of the limitations. We looked at the recost area. We went through everything. Okay? We did an analytical study by grade of everything in the mill. Chips, digesters, washers, bleach plant, O2, kilns. What is the effect of going on a grade through the process? Okay, so we could see every change and what was driving it. What was changing? The organic-inorganic ratio we know is changing. The length of fiber is changing. The fiber content of the liquor is changing. You name it. It's all changing. And you can see all the different grades as we were going through. Then we looked at the liquor chemistry changes by grade. What's different in the chemistry of the liquor? And there was differences in everything. I just showed a couple, but we were showing everything we could look at. How is it different? Okay? Then we put together a map and we started working through all the different issues. And we were estimating, okay, if I put the chips on here, when am I going to see it halfway down the digester? When am I going to see it at the blow line? When am I going to see it at the bleach plant? When am I going to see it? How do I adjust the alkalinity to compensate? How do I adjust CLO2? How do I adjust all these things, right? And we started to look at predictive, not AI. AI was here, okay? So it was just, how can we see these trends? We can see the things moving. How do we predict it and get ahead of it? So the operators can see it clearly. They know when to operate, okay? Then we had to come back as a chemical supplier. Our chemistry had to be automated because what they needed for defoamer on high kappa softwood, and suddenly I'm going to cold pulp bleach, it's totally different. So how does the specialty chemicals react, and how can I use those to help stabilize the transitions? When it all got said and done, we added $450,000 of specialty chemical cost because we want to make sure we're putting the stuff in where it belongs, what belongs. We had some chemistries only on some grades to optimize the chemistry, the reactivity. But at the same time, they put in their pocket $5 million, okay? $5 million per year. And we still have projects we're working through. It's going to be more than that. But right now, they have $5 million that they can account for hard money, not the funny money sometimes we calculate, right? This is real hard cash. So it's possible, but you really have to change the way you think. And that's really the purpose of my talk today. I want you all, there are technologies out there. I'm hearing about some wonderful stuff. But for those of you running a mill, what can you do with what you have today? And I think you haven't even started to unlock that potential in many cases. Start to think hard about what can I do to be better at what I do today than I was yesterday. And that to me is how you get to these final points.
So in summary, 5 minutes more.
Yep. In summary, sustainability, please use it correct, okay? Don't just, stop when you're driving home and hug a tree. And it's about being profitable. Everything you do at the end better be profitable or we are no longer sustainable no matter how much you've helped the environment, okay? That focus has to go beyond centerlining. It's not just do a little better at what I was doing. You have to look hard. You have to dig deep on what is different. What do I need to do different today, okay? You have to take an honest, hard look at what you're doing today and where are your weaknesses. And that's what we need to address hard, okay? And getting at variability, getting at liquor chemistry are two of the biggest cost savings that you will find, okay? There is variability that's good because I'm driving it, okay? My very first superintendent when I started said there's only two options. I can run my process or my process can run me. Okay? Run your process. Own it. Change it. Drive it. That is the main message I had for you today. Thank you.
Time to questions. I invite the presentations to here. It's more easy. Any question?
Good afternoon. And very nice presentations. Good messages also. So, sorry, I don't know your names. I was saying from the last presentation. That we need experience, of course, many years in the field to start feeling the process. I know what you were saying. I am there, but how do we know to centerline or to maintain the sustainability? Sometimes it's very difficult to, as you said, sometimes we are a bit in the middle of a bridge. We don't know which direction we should go.
Yeah, for me, it usually starts out with, what is it that I'm having trouble doing today? What is it that's costing me a lot of money today? What is it that I'm having trouble meeting the customer need today or his future need? Always the customer's asking for better pulp, stronger pulp, brighter pulp, but doesn't want to pay for it, right? So how can I meet those goals? So sitting back and saying, okay, what is it that I do well? You have your own financial analysis in the mill. You know where you're doing okay and where you have opportunity to improve. You know where you have a lot of variability. Sit down and look and say, why is that? And am I really working on what's driving it, or am I just looking at the final number? And that usually determines what I'm going to start to focus on. Almost every mill when I go to, if I start asking questions, I start to hear terms like, well, I do get limited once in a while by the evaporator. Oh, I do get limited sometimes by the recost area. So usually if you bring that up, if it is an issue for you, it's a restriction for the mill at times. Usually that's a warning sign. So a lot of times those are areas that we begin with. And then once you start to dig deeper, you'll all of a sudden start to uncover a lot more things than you thought you had. But those are usually the kind of things I'll look at. Where do I have trouble meeting what I should do? And also, where do I run into restrictions in the mill at present?
One other thing that sometimes we have some difficulties is we are the pulp guys. There's the paper guys. And sometimes the pulp guys give some variability. And the paper sometimes don't understand why this really appears.
Correct.
And sometimes it is difficult to oversee everything. I don't know if you're following me.
Yeah, it happens. But that's where leadership of the mill needs to step in, right?
Of course.
And that's really the challenge. But I think again, we have to be very honest. I think a lot of times we're not always so honest with ourselves. Nobody wants to say my area has a weakness, right? Nobody wants that. But unless we do, I think you're going to always have that challenge.
Okay, thank you.
Yep.
Any questions more?
Hi, everyone. Thank you very much for presentations. This one is for Heikki. Well, we already worked a bit, but it was very good presentation. Regarding this shutdowns behavior, you stress the situation where we have very low loads during the period, but it's also common at the start of the shutdowns that we have kind of peak loads, and it's, at least in our mills, it's common to have that due to the washing and did in this type of work did you observe any reaction to these peak events before the shutdown and the going down, and if it's possible to see it through the microbiology? And the other question, it's very interesting. Okay, it's well known that if you don't have food, usually the first ones to disappear is the filamentous. If you have, for instance, enough emergency capacity in basins, it could be a technique to try to solve a strong filamentous problems, to derive for some hours the effluent and try to get these filaments controlled and then go back picking up the effluent this way. So these 2 points just to comment. Thank you very much.
Okay, thank you, Luis, for good questions. Of course, the kind of shutdown, when it begins, we see a lot of peak loads. Usually it's a matter of control strategy. You can increase return sludge flow if you have capacity. Somehow try to minimize the heat. Of course, if you have something, but if we think about the sludge that is in rotation, it's grown there for, let's say, 2 weeks or something like that. We have 100 tons of biosludge. So if it takes heat for 1 day, you don't see much in biosludge structure. You might see peak loads coming through. But if you think about how much sludge you have in the system, it's really changing slowly. And this is pretty much the case that usually we don't see that in the sludge structure that much. We can see it in other parameters, of course. And when it comes to filament control, what we see often is that the basins become too small because, let's say in Finland, wastewater treatment plants were built in 1990s, pretty much 30 years ago, and now they have increased production. So we see a lot of too small basins that are overloaded, and then you don't have much to do unless you can increase the capacity. But if you have enough space, you can of course think what I could do with the control. Maybe you have room to increase sludge concentration to give flocks better dominance, but it's always an issue of process design also.
Thank you.
Time for one question more. The members who have that form in our envelope, please go to the secretary to pick the book. The book is the Tecnicelpa, the story on the pulp and paper. Question, please.
This is going to Isabel, so thank you for her very nice presentation. Very structured and something very objective as well. As you move along the presentation, I had some questions. Most of them you answered as you moved along the presentation, but in two part of the presentations on the paper side, it seems obvious that we're going in the right direction using that on the chlorine dioxide sequence. But just for our sake of curiosity, what would be the impact of using that water in terms of reduction of water and specific water consumption on the pulp side of the mill? So that's one question. The second question relates to the usage of condensates from evaporation. And you've done laboratory trials on the bleaching where you compare the condensates by using a reference of hot water with condensates. Of course, on real-life mills, you'll have the washing filtrates on the bleaching sequence, which might have some difference from the reference that they use. So just to think if you have thought about the implications of that, and because the potential would actually be on the upside in terms of the impact that might have.
Okay.
So these two questions, sorry.
Thank you, Gabriel. I'm going to start with the second because we tested the condensates to replace the hot water in a place where we use hot water. So we are simulating the real process. In most of the washing stages, we use the filtrates, counter current mostly. But in this case, we use the hot water in the mill, and some of the mills, they are not all the same in the Navigator, but we use hot water, and that's why we use hot water as a reference. As for the estimation of water reduction, because we use still hot water in bleaching, the maximum reduction would be the total replacement of this hot water. First, I don't know if we could go all the way because we are closing the circuits and we have other impacts of accumulation. And the other limitation is the secondary heat recovery. So reducing hot water doesn't always mean that we reduce fresh water, because we still have to produce hot water and recover heat from the cooking. So we have to have ways of dealing with this heat if we want to turn this reduction into actual reduction of water use in the mill. That is good.
Just on the paper side, I mean, the impact of that measure will account for 1 cubic meter per ADT, or
if it will reduce the wastewater in the paper side and globally. If we use that, the case I showed that we are using, and we are currently using in one of our mills, we are using to replace fresh water, fresh heated water, in the washing of the transferred pulp. We account that water to the paper machine. So it's an actual reduction, and we have the numbers from this paper machine. It was about 2 cubic meters per ton of the paper machine. But if we produce market pulp in the same mill, we have to take that into account, especially the OBA.
Thank you.
Okay, the time fly. Stay 10 minutes later. It's time to coffee break.